This video is going to be the first video to look at sections 9.3 to 9.5. Section 9.3 looks at significance test about a mean. Previously, in section 9.2, we looked at significance test about proportions, and we looked how to conduct a significance test for a single proportion. In these examples, we're going to look at how to conduct a significance test for a single population mean. And what you should notice is the steps are very similar to what we did with proportions. We just need to make some changes to account for the fact we're working with a mean now instead of a proportion. So let's look at the basic steps together. First of all, we're going to check our assumptions. In order to use the formulas for a significance test, we first need to confirm that the sample is random and that the population data is normal. One way to do this is to either be given that the population data is normal, or we could look at a histogram of the sample data, or stem and leaf plot, or other visualization of the sample data to see if there's any evidence in the sample that the population is not normal. If the population is not normal, or we're not given any information to determine that, then we need to the sample size requirements for the central limit theorem. For a single mean, we need to check that the sample size is at least 30. After we check our assumptions, we need to state the null and alternative hypotheses. The null hypothesis will be listed first. When you're working with a mean, the hypothesis will include the symbol for the population mean, mu. Next, we'll calculate the appropriate test statistic. Here, our test statistic is given by t, and our test statistic is calculated by taking the sample mean minus the value of mu under the null hypothesis divided by the standard error. So here, we have that x bar is our sample mean. Mu naught is the value of mu under the null hypothesis, and then s divided by the square root of n, that is the standard error that you saw earlier in Chapter 8 when we calculated confidence intervals. Next, we'll find the p-value. We'll do this by comparing the test statistic to a t-distribution with n-1 degrees of freedom. We'll use a t-table to give us a range of values for the p-value. And on page 11 is a discussion of which area under the curve will correspond to the p-value. This is the same discussion that we already had when working with proportions. For a video on finding different p-values from a t-table, you can watch this link right here. And then finally, we're going to state our conclusion of the test in context of the problem. So let's look at several examples. Example: a coffee shop relocates to Italy and wants to make sure that all the lattes are consistent. They believe that each latte has an average of 4 ounces of espresso. If this is not the case, they must increase or decrease the amount. A random sample of 25 lattes shows a mean of 4.6 ounces of espresso and a standard deviation of 0.22 ounces. We're going to use alpha is equal to 0.05. So we're going to start out by listing our assumptions. So one of the things we need is a random sample. And here we have that it's given in the problem that we do have a random sample. Next, we need a normal population or we need our sample size to be bigger than or equal to 30. Notice this was the same assumption that we needed with means when working with confidence intervals. No information is given about the population. And n is equal to 25, which is less than 30. So we are going to proceed with caution. Next, we're going to state our hypotheses. Remember, we always list the null hypothesis first and the alternative hypothesis second. Remember that our alternative hypothesis is what we would like to prove. So notice what they're trying to find out here is they believe that each of the lattes has an average of 4 ounces of espresso. If this is not the case, they're going to have to decrease or increase the amount. So what they're going to try to prove here is that mu, that population mean, differs from 4 ounces. Because if they can prove this, then they're going to need to, again, increase or decrease the amount. And then under the null, we're going to assume that mu is equal to 4 ounces. Next, we need to calculate our test statistic. We're going to start by just writing down the formula. And again, this formula comes from the previous page. So now we need to go and identify each of the different pieces that we need. Well, remember that x bar is our sample mean. Well, here we're told a random sample of 25 lattes shows a mean of 4.6 ounces. So this 4.6 is our x bar, and it goes on to say, and a standard deviation of 0.22. So this 0.22 is our sample standard deviation. So looking at our formula, we have that x bar is equal to 4.6. We need the value of mu under the null. Well, under the null hypothesis, mu is equal to 4. Sample standard deviation, which again is 0.22, divided by the square root of our sample size, and we had 25 lattes in our sample. Take a moment and place this value in your calculator. So in the numerator, we're going to have 4.6 minus 4, which is equal to 0.6. And in the denominator, we're going to have 0.22 divided by the square root of 25, which is 0.044. Then taking 0.6 divided by 0.044 gives us a test statistic of 13.64. Next, we need to find our p-value. To find our p-value, we're going to compare our test statistic to a t-distribution. So we need a t-distribution with n minus 1, which is equal to 25 minus 1, which is equal to 24 degrees of freedom. Visually, what this would look like is, recall the t-distribution is a bell-shaped distribution symmetric at 0. Compared to the standard normal distribution, it has wider tails. So this is a t-distribution with 24 degrees of freedom. Notice we have a two-tailed test here. So what we're saying is if we place our test statistic, 13.64, down here, and we get the area to the right, and then since it's a two-tailed, we place negative 13.64 down to the left and shade in this area. The shaded area is the p-value. Now, what we're able to do using our t-table is to find a range of reasonable values for this area. So we're going to look at our t-table, which I have a copy of here, and recall that we needed 24 degrees of freedom. Looking at the row that corresponds to 24 degrees of freedom. Next, what we're going to do is find two values that our test statistic falls. This corresponds to 0.001, so this tells us our p-value will be less than 0.001. If our p-value is less than 0.001, then we know automatically that our p-value is less than 0.05, since 0.001 is less than 0.05. Therefore, we're going to reject the null in this case. Now we can write our interpretation. And here we say, at the 5% significance level, we have enough evidence to conclude that the mean amount of ounces of espresso sold at the shop differs from 4 ounces. And notice in particular, based on the sample, they are over-serving. And we know this because the sample mean, if we go back to our sample mean, was 4.6 ounces. Let's look at another example. Unfortunately, arsenic occurs naturally in some groundwater. A mean arsenic level of 8 parts per billion is considered safe for agricultural use. A well in Texas is used to water cotton crops. This well is tested on a regular basis for arsenic. A random sample of 35 tests gave a mean of 7.2 ppb arsenic with standard deviation of 1.9 ppb. Does this information indicate that the mean level of arsenic in this well is less than 8 ppb? And we're going to use alpha is equal to 0.01. We're going to start out by checking our assumptions. First, we need a random sample. And notice we can say, yes, this is given in the problem. Next, we need a normal population. Or a large sample size. Here, we're not given information about the population, but we are given that our sample size N is equal to 35, which is greater than or equal to 30, so therefore the central limit theorem applies. Next, we're going to write out our hypotheses. Recall when writing out our hypotheses, we always write out the null and then the alternative. The alternative is what we would like to prove. So the question asks, does this information indicate that the mean level of arsenic in this well is less than 8 parts per billion? So here we're going to test to see if mu is less than 8 parts per billion. And under the null, we'll assume that mu is equal to 8 parts per billion. Now that we've got our hypotheses, we can calculate our test statistic. We're going to start by writing down the formula. Next, we need to identify each of the different pieces. So notice up here, we're told that a random sample of 35 tests, so 35 is our sample size, gave a mean of 7.2 parts per billion, so that 7.2 is our x bar, with a standard deviation of 1.9 parts per billion. So notice the 1.9 is our sample standard deviation. Filling in the pieces down here, we have x bar is 7.2. Under the null hypothesis, mu is equal to 8, divided by 1.9, divided by the square root of 35. Placing these values in our calculator, in the numerator we're going to have negative 0.8, and in the denominator we're going to have 0.3212. Dividing these numbers, gives us a test statistic of negative 2.49. Now that we have our test statistic, we can find our p-value. Notice to get our p-value, we're going to need to compare our test statistic to a t-distribution. Here, we need a t-distribution with n minus 1, which is equal to 35 minus 1, which is equal to 34 degrees of freedom. So if we were to draw this t-distribution, again, recall that t-distributions are centered at 0. So this is a t-distribution with 34 degrees of freedom. Here we have a left-tailed test, and our test statistic is negative 2.49. So the area to the left here will be our p-value. Next, we're going to use our t-table to help us find this value. So looking at our t-table, we need a t-distribution with 34 degrees of freedom. Notice that the value 34 is not one of our options for our degrees of freedom. So just like when we worked with confidence intervals, we're going to round down to the closest value. So here we will need to round down to 30. And next, I want to find two numbers that my test statistic is between. To do this, you'll use the positive value or the absolute value of your test statistic. Since our test statistic was negative 2.49, we're going to find two values that 2.49 falls between. Notice that 2.49 falls somewhere between these two values. Moving up to the top of the page, looking at the one-tailed options, which are these two right here, this tells us that our p-value falls somewhere between these two values. Using those two values, we know that our p-value must be greater than 0.005, but less than 0.01. Notice that our alpha in this case was equal to 0.01, so we know that our p-value is less than alpha. So in this case, we are going to reject the null. And now we can write our conclusion or our interpretation. the first video for Chapter 9.3 through 9.5.